we just had an excellent colloquium by Alycia Weinberger, who's sitting somewhere over there. And she will talk a little about something else in a few minutes. We'll start with Brian Loomis, who is familiar to all of us, and he's now at NRAO. Used to be a student in our department. And he will talk about misaligned protoplanetary disks, evidence for planet-disk interaction. Then we'll continue with Duane from MIT, who will tell us about playing your cards right, leveraging one-shot galactic chemical evolution models to understand and predict chemical abundance ratio distributions in all the galactic systems. It's a very long title. Very big guy. And then we'll hear from Alycia, who will tell us about astrometry of low-mass objects. Are these stars or?
Stars and roundwork.
Okay, we look forward to that. And then finally we'll hear from Eve Lee from Caltech, that will be the CFA colloquium speaker later today. And she will talk about the balanced budget view on forming giant planets by pebble accretion. Right.
Thanks, Avi. It's great to be visiting back in Cambridge. So today I'm going to talk about misaligned protoplanetary disks, and in particular how this might show some evidence for interactions between planets and disks at early stages. But rather than talking about the disks to start with, I want to introduce this from the exoplanet side. And so many of you are probably familiar with this plot. It shows the evidence for the Kepler dichotomy, which essentially is an excess of single systems that are observed by Kepler. And there's a number of different explanations for why this might be. You could think that there might be a reason why you would preferentially form single planet systems. But another explanation is that it's simply a viewing geometry effect. And some systems that you're seeing have coplanar planets, and then you're able to observe multiple planets. And then some systems have one planet that might be non-coplanar with the rest, and so then you'd end up with an excess of single planet systems when you observe them. So if that is the case and you really do have a misalignment then between some of the planets and the rest of the coplanar planets, then you think about, okay, how do we form that? And so there's been a number of different proposed explanations for how you might form this, but a lot of them boil down to spin-orbit misalignments and how you can essentially excite planets up in the system. And so it would be really interesting to think about that in the context of during the disk stage of star and planet formation and what's happening in the disk. Do these misalignments occur early, or do they occur later once the disk is dissipated? So it's really interesting to start to constrain what the geometries of these disks are. And the first constraint that I actually want to talk about is also coming from photometric surveys. So this has been known for quite a long time that there's these systems that show this periodic dipping behavior, the so-called dipper systems. And all the way back in 1999, this was supposed to be due to, this is the inner disk, so only a few stellar radii. The magnetosphere of the star can lift up material and warp the very inner regions of the disk. And this warp here can then process around, rotate around on the stellar rotation time period, and then it will cause shadowing out onto the rest of the disk. And then in addition to the shadowing that it causes, it'll also periodically occult the star. As it occults the star, this will modify the light curve that we see. And so if this is the case, that this mechanism is responsible for all of the dippers, then what that constrains is it constrains the viewing geometry for all of these systems. We know that dippers are about 20% of all YSOs. And that's in good agreement with an idea that this is basically all edge-on systems, or close to edge-on, plus or minus, say, 15 degrees from edge-on. That would be consistent with about 20% of objects viewed at a random orientation. But what's interesting is when you start to compare this with new ALMA constraints and you look at the outer disks of these systems, they're not all edge-on. And actually, Megan Ansdell in 2016 showed that the distribution of outer disks for these dipper systems is consistent with a completely random orientation of the outer disks relative to the inner disks. So this poses the question, okay, how do you have either this mechanism here, which has been long supposed to explain the dippers, is incorrect, or the inner disks and the outer disks are misaligned? So if we proceed with the hypothesis that the inner and outer disks are misaligned, we went back and we looked at the archetypical dipper system, AA tau. So this is the one that Jerome Bouvier looked at in 1999. It's the archetypical system for this class of objects. And indeed, it is also modestly inclined. It's not viewed at an edge-on viewing geometry. So this is our proposed system geometry, and we also have additional constraints from the kinematics of the gas, and we have additional constraints from the jet of the star to show that the inner disk, or at least the stellar alignment, is misaligned with the outer disk here. And we think that the misalignment angle is roughly about 45 degrees or so. So if we think that we have evidence then for these misaligned systems, we can start thinking about what possible predictions would that have for other observables for the systems. So one observable that predicts is that you'll have shadowing out onto the outer regions of the disk. So this is a cartoon from Mineral 2017 that shows that if you have an inner disk here, which is exaggerated in size just to show you the disk, the shadowing from that will then cause these slight pinched regions in the outer regions of the disk. And this is showing what that would look like for scattered light observations of the disk. In addition, there would be velocity perturbations from the inner disk. And so you have a warp in the gas, and that warp then causes deviations from Keplerian rotation. This is a moment 1 map to ALMA data, which shows you the Keplerian rotation from the blue shifted side to the red shifted side. And this kink in the center is the perturbation that you would see to that velocity field if you did have a warp. This is degenerate with signatures of infall, though, so I'm not going to be talking about this today. There's quite a large body of work that's been done on these sorts of velocity perturbations. But what I'm going to talk about today is this shadowing effect. So you would expect then that you would see these shadows out here in the scattered light observations, and that's exactly what we see from this wonderful zoo of sphere observations. There's this huge variety of different morphologies to the disks. There's spirals, there's these really strange patterns here, and we can see that there's these pinched features in a number of the disks, and those pinched features are essentially what the shadows should look like. And the reason that they're not exactly 180 degrees misaligned from each other is due to the fact that the disk surface is flared, and you're seeing this in the small grains for the scattered light. So disks like 142527, 453, these all show these evidence for the shadowing in the scattered light. So we went back and we looked at our A tau observations then, because if we see the shadowing in the scattered light, you would think that you might also see this shadowing in the millimeter continuum that we observe with ALMA. And indeed, it looks like there might be some small evidence for shadowing here and here. You would imagine that for a fiducia model with no shadowing at all, these depressions would be due to just the inclination effects, and they would be symmetric along the minor axis, but they're actually slightly misaligned from the minor axis. But at this resolution, it's hard to tell. It's hard to tell whether this is a beam effect from the convolution with the beam. So we went back and we looked at this at much higher resolution. Now we're able to resolve the inner disk, and we're able to start seeing that this is clearly due to shadowing across the disk, very similar to the features that we see in scattered light for these sorts of objects. So we compare this to a fiducia model, and you can see very clearly that there's that shift and twist. And then we run some radiative transfer models to show that if we actually include a misaligned disk and we self-consistently calculate the radiative transfer, we're able to essentially lower the temperature of the dust grains in these regions. And when we lower the temperature of the dust grains, then because the dust is optically thick, it translates to a depression in the flux. So we're able to reproduce this quite well with a misaligned model. Something that we're looking at now, though, is how well can we actually constrain what the misalignment angle is. So we now think that we have pretty clear evidence that there is a misalignment, but what is the exact numerical misalignment? And it turns out that actually at the resolution that we have currently, we're not able to really distinguish between a number of different scenarios, a 40-degree misalignment, a negative 40-degree misalignment, or even up to 75 degrees. At the resolution that we currently have, these models are pretty much indistinguishable. But we have an accepted cycle 6 ALMA proposal to go back and look at this at much higher resolution, and that will allow us to actually resolve the inner disk and distinguish between these different scenarios. So here I'm showing the actual azimuthal profiles for these models and the disk here. And we can see that the shadowed model does a much better job of reproducing the profile. But what we'd really like to be able to do is not have these sorts of inclination effects when we're looking at this. A face-on object would be a lot easier to see these shadows in. So we also went back and we looked at, okay, so Megan Anstill showed that this object is supposed to have a misalignment. And so we went back and we looked at archival data for this object as well. We re-reduced the data and we showed that there's also dips in this object, J1604, as well, showing clear evidence for an inner disk shadowing regions here and here. Now what's really neat about this is that we're able to show the dips here, but then we can compare that with scattered light observations that have also been taken for the object. So there's a recent paper that came out by Pania et al. That shows that in sphere observations of the target, those dips actually move around slightly back and forth. They stay in roughly the same spot, but they do change in morphology over time. And so this gives us our first hint at what's actually going on in the inner disk. Is the inner disk a permanent object that's not really changing at all on these time frames, or is it moving around? Is there accretion streams that are then modulating the shadowing here? So that's something that we're starting to look into. And we also are now able to look at this with the ALMA data as well. So we have another set of observations, and so now we have 2 epochs for the ALMA data on this source. And we do see that there's some evidence for a slight shift in the location of the dips and some evidence for a change in the morphology of the dips. So we also have an additional accepted ALMA Cycle 6 proposal to look at this disk at much higher resolution and to also get a 3rd data point for this. So with this, I want to summarize by saying that what's interesting about these observations for AA tau and J1604 in particular is that this is showing that for single T Tauri stars, we're able to see this sort of behavior and that it occurs really early in planet formation. So we're not limited to only binaries or higher mass stars. When we think about the mechanisms for how you might cause these misalignments, it's quite easy to do this for binary systems, but it's not so easy to do it for single stars. You need some sort of perturber in the system, and it's difficult to do that with a planetary mass object. But we think that constraining the misalignment angles directly with our new ALMA observations will allow us to start comparing with model predictions. And the other thing that we really want to do is we want to start getting a better handle on the demographics. So we have another proposal in as well to go back and look at all those dipper systems. And by looking at those dipper systems, we can start to get a better handle on the distribution of misalignment angles. And by having a distribution of misalignment angles, we can compare those back to different disk formation models and see how those compare. And then eventually the goal will be to compare that with the distribution of misalignment angles predicted by models to explain the Kepler dichotomy. With that, I'll take questions. Yeah. So I'm not an expert on the exoplanet statistics for that. I think there's people in the audience who know much more about that than I do. But what we are really trying to get a handle on is we're trying to get a handle on what the distribution of these misalignment angles is. We really want to know, are we forming disks that have misaligned inner disks that stay permanent throughout the lifetime of the disk, or are these transient inner disks? It turns out that actually there's a lot of evidence that the inner disk for J1604 is actually a transient feature, and that the near-infrared evidence for this inner disk here, you can't even see it in the ALMA observations, shows that it might be transient. Whereas in AA tau, it's clear that there's a permanent very bright inner disk. So those are 2 fairly distinct objects, and they would have pretty different ramifications for, say, planet formation within that inner 3-5 AU. So I think that what we really need to do is get a better handle on the demographics of these sorts of objects by looking at them in scattered light and with ALMA before we're able to really have any handle on how that translates into predictions for exoplanet formation models.
Forgive me because I'm not an observer, so my system is totally wrong. But earlier you had one instance you mentioned HD142527, which I think is known to have a binary, a misaligned binary.
Yes.
So have you looked at whether or not that's consistent with the shadowing?
Yeah, so it is. And so that object, part of the reason that I emphasized the AA tau and J1604 are single T-Tauri stars is that they're actually quite different than from HT 142527. There's been a lot of papers on this object explaining how you can form this sort of misalignment for that, and it's easy to do that for binary systems. What's kind of tricky with the objects that I'm presenting is that they're single systems, so it's much harder to explain how you might go about that. But yes, it's well known for a number of these objects that are higher mass and binaries that you're able to do that. But yes, those have definitely been investigated pretty deeply.
Just an observation, the top right sphere guy has 3 shadows.
Mm-hmm. So I think that these may be artifacts in the imaging. I'm not a sphere expert, but I know that some people have speculated that this may be artifacts in the imaging. However, I should note that one thing that's quite interesting is that there's been some suggestions that the shadows here, or sorry, the spirals are actually launched at the location of the shadows. And there's been a number of discussions as to how pressure perturbations that can occur because of the shadowing might lead to the formation of those spiral arms. Okay. I think Eve had a question.
Do you have a sense of what is the required size of this inner disk?
Right. So those are two things that we're investigating with our ALMA program for both AA tau and for J1604. So with AA tau, because we know that the inner disk is probably optically thick, we're able to constrain at maximum the size here is about at minimum the size of the inner disk is about 3 AU. And it needs to be at least that large, which is why we know that we should be able to resolve it with our proposed new observations. And then for J1604, we don't see the inner disk at all, but we can get, by having much higher resolution ALMA observations, we'll be able to put a good upper limit on the flux there. And then through radiative transfer modeling, we'll be able to bound the amount of material there by constraining on one side from the near infrared and on the other side with ALMA observations. So we should be able to get a measurement of the total dust content there as well.
Okay, great. All right. So I'm probably going to change up the subject matter a little bit from the rest of the talks. I work on galactic chemical evolution. It's basically in the context of galactic archaeology, which is a new burgeoning field. And some of the focus of this field is to understand the accretion history of the Milky Way and other nearby galaxies by looking at resolved stellar populations in terms of their chemical composition as well as their dynamics. And basically, I've focused purely on trying to understand and expand ways in which we can understand chemical abundance ratio distributions to leverage that information in terms of understanding the accretion history of the galaxy as well as star formation histories within dwarf galaxies. So this sort of brings up what is galactic archaeology, in addition to a couple other subfields of this work, which is stellar archaeology, otherwise sometimes referred to as dwarf galaxy archaeology, in which you look at the early history of the universe based on its early stellar chemical composition. Galactic archaeology is concerned with looking at the formation and evolution of the Milky Way and other nearby galaxies. We're now pushing out towards Andromeda in terms of observing enough chemical abundances in certain stars there. You can start to play that game out there as well. And of course, last but not least is this sort of field, the other side of the coin, which is near field cosmology. And it's the idea that if you can lock down some better understanding of the accretion history of the galaxy, you're now probing galaxies that lived long ago, and you have access to that information, which is harder to come by if you look in high redshift surveys. So if we put this into a context of some schematic or image, you have the history of the universe, and these three subfields of galactic archaeology in general probe these different epochs of formation and evolution in the galaxy. So if we want to put this in the context of galactic chemical evolution, the simplest way of looking at it is you have your initial gas cloud in the early universe, and you start to form the first stars. And of course, those stars are essentially metal free, so we call them POP3 stars. And also you get a few of the extremely metal poor stars. And I'll tell you a little more about the specifics of those definitions. But the main thing is that in the smallest galactic systems, you can actually get the enrichment from the first stars preserved. And that's in these ultra-faint dwarfs, which I'll get to. But also what's interesting is in some of the more classical dwarfs, if you look at the extremely metal poor end, which is, we define that as stars with abundances of Fe on H below -3, so a thousandth of the solar metallicity, that you can also get some understanding of what's happening in the first stars in those populations as well. Moving on, you see that both the gas and the stars become much more metal rich over time, depending on their star formation histories. And all this leads to the type of systems that we see today, particularly in the ultra-faint dwarfs, in the dwarf spheroidals, where essentially you have fossilized remnants of star formation that's happened long ago. And so we can overlay exactly these same subfields in terms of where the primary focus is. So I don't have enough time to go into detail about some of the projects that I've worked on to understand stellar and dwarf galaxy archaeology, as well as galactic archaeology and near-field cosmology. But I will drill down a little bit on some preliminary results I'm working on currently, and just give you a quick overview of what I've worked on in the past. So in terms of stellar dwarf archaeology, what was great is a few years ago, there was the discovery through the Dark Energy Survey of the first superabundant stars in barium and europium. And many point out, particularly Professor Anna Frabel, that this was actually the first detection of a neutron star merger. And but interesting enough, the jury's still out, because the certain rare core collapse supernovae are making a comeback in terms of the possibilities here. But the cool thing here is that in my work in 2013 with some simple galactic chemical evolution models, which I call these one-shot models, to try to understand the chemical abundance signatures in ultra-faint dwarfs, I was able to come up with an estimate of the number of stars that you would have to observe across all ultra-faint dwarfs before you would see such stars. And basically the prediction was spot on. We observed, I made a prediction when we had 6 ultra-faint stars observed, and then basically we've gone up to about 30, and that was roughly the prediction that I gave on that. And so this is the dwarf galaxy archaeology part, and this is the stellar archaeology part, which is that basically you can look at individual abundance signatures and look for what's either the S or the R process pattern. And that's what was seen in these 4 stars, that it was a distinct R process pattern, which is associated with neutron star mergers or other rare events. So moving on to galactic archaeology, one of the things that I also wanted to understand is if we have this distribution of stars that were donated through mergers over time, and they have their unique star formation histories, which led to unique chemical abundance ratio distributions, could you leverage that information in their long-lived chemical abundances to understand and pull out the accretion history of the galaxy? And so in a proof of concept study with the Bullitt-Johnson models, basically we have one halo realization here, and I've color-coded it in terms of the relative contribution from various satellites. And what you see is that it's mirrored in the actual observations done a decade earlier, where you could see low-mass dorsal sit in a particular part of a chemical abundance space here, along with more massive things like Sagittarius and these red stars. The green are the halo stars, and the blue are the light blue is the SMC or the LMC. And so you can see that because they lie in these unique parts of chemical abundance space, there might be a way to back out what the accretion history was. And so in order to do that, we basically looked at what's called the expectation maximization algorithm, treated halos as a generative mixture model of a set of different dwarf galaxy templates. And then in doing so, we're able to show that in theory, you could use this technique to understand the luminosity function of things that accreted over time. Okay, so now getting to our final results here. The project I'm working on is piggybacking off of the 2013 paper, adding in rates for neutron star mergers. And in doing so, you create these models of probability density distributions in chemical abundance ratio space for any sort of given element you're interested in, or element to abundance ratio. And so you get these distributions just based off of stochastic sampling of the IMF. When you select fewer stars from the IMF, you get more incomplete stochastic sampling that allows you to broaden the distributions that you see. Conversely, if you sample more, you get a narrowing of those distributions. So if you combine the recycled hydrogen gas you get in the models, and here the models are signified by the amount of stars that you select from the IMF at any given time. You see you follow this trend where basically you get this nice fit for your recycled gas. You need that in addition to some reservoir of gas, so your sort of dilution mass, to get a sense of where your abundances are going to lie in the next slide. In addition, you fit basically a function to the abundances here, which is strontium over europium. And the idea is that strontium is a proxy for enrichment due to supernovae, and the europium comes from the neutron star mergers. And your individual dots here are the averages and medians of the models used. So finally, second to last slide here. Basically, this is what one of the models looks like. Here's your probability density distribution in chemical abundance space. And on the x-axis, you have europium over hydrogen. And so what you're measuring here is a proxy for the amount of dilution mass, the amount of hydrogen you have to add to move the model right or left in this chemical abundance space. Here, these stars are newly observed stars that are R process enhanced stars. So these are stars that definitely have europium from the R process. And what you see here is that basically in the limit of you assuming that there's one neutron star merger that went off in these systems, the difference in the strontium abundance is basically you counting up the number of supernovas that happened in these different systems. So this is the most massive system that I look at in terms of my models. And so it sits up here in abundance space. The lower mass models will sit here, and you can literally count off the number of supernovas that most likely went off in these systems. So here I'm just plotting all of the data that we have from this particular database for halo stars, for some of these R2 and R1 stars I showed you previously. And the one thing I want to point out with the remaining time I have is these lines here are lines of constant star formation rate. Star formation efficiency, excuse me. And that just comes from the theory and the models that I use. And what's interesting is if you color code the data by its metallicity, it actually tracks rather well with the actual star formation efficiency. So this is basically a new result that people haven't looked at in the past, and trying to understand exactly what's going on here in dwarf galaxies would be very useful. So basically, this is I'm giving this all to be some food for thought, and with that, if you have any other questions, please let me know. Thank you. That's a great point. Yeah.
One question with respect to the possibility of neutron star mergers, there is this delay time for the two neutron stars to come together, and when you go back in time, when redshift 6 or so, the first stars, low metallicity, below -4 or so, then the universe was pretty young, and there is an issue of how to make binaries that are so close to each other, and the two universes are so close to each other.
Yeah. So yes, I completely agree with that. And actually, that's sort of been a hang-up for me in the field. There's been a lot of focus on the neutron star mergers and trying to find these rather fine-tuned arguments to look at the tails of the distributions for mergers to get them to actually go off soon enough to actually enrich these very ancient stars. And so now the community is pivoting towards these collapsars as a possibility, that they're actually rarer than neutron star mergers, but they actually might produce more, which is very interesting. And it also might predict the differences between the R1s, which are the R1 square neutron star merger stars here, versus perhaps these triangles are found in ultrafaints, and these are R2 highly enhanced R process stars. It might be that you're more likely to get the neutron star mergers in the classical dwarfs and the magneto or collapsar, jet-driven supernovae in the lower metallicity ultrafaint counterparts. So.
Sorry, how sensitive is your analysis to rates of both the collapsars and neutron star mergers? For example, would your conclusions change a lot if you had 10 times the number of collapsars or neutron star mergers?
That's a great question. So one of the things that I looked at, so I in this plot, I basically made sure I picked a rate low enough that I would always get one neutron star merger in the probability density distribution. But if you up the rate, one of the things that happens is that this distribution lengthens, and that shows the lengthening is due to the broadening of the number of the quantity of europium that can be injected into the ISM. That's because you get now interplay between 1 or 2 or 3 neutron star mergers. Likewise, with the collapsars, we believe that there might be 3 to 5 times more proficient in producing the R process. That might get you something like half a dex difference. So I'm still working out exactly how you would see that. Obviously, there'd be some overlap at some level, but if the rates are different enough, you would see, which is basically what I was trying to point out here. You might see a difference in where they predominantly enrich stars. Yeah, thanks. Oh. Yes. Sorry, I was like hoping my answers were quicker. Sorry. Yeah. So. If there was what? Well, if there's no natal kicks, then it would make it more. No, I haven't. Yeah, so I'm pretty agnostic. So there's indeed you are one such expert in this in terms of doing the hydrodynamic simulations, but coming more from a theory semi-analytic framework. what I try to do is look at the data and make the model sort of data driven, and say this is what the universe is telling us. Here are the constraints. Now given those constraints, how well does your particular model for neutron star mergers or collapsars or whatever work within this framework? So.
MIT is not very far from us.
Yes.
Other discussions are as well.
Yes. Yeah. Thank you. Dongle? Oh, the extension? Do you have the? It's right here. Yeah, I have an older. Oh, and the mic.
You'll see my slides, but you'll hear him. Okay. Oops. Oh, anyone want to look at white dwarf spectrum? Okay, so for now, for something completely different, I wanted to tell you about an astrometric planet search program that we've had going for the last 11 years and why you would want to do such a thing. The person who spearheaded this project from the beginning was Alan Boss, and that's a picture of our camera on the right there. It's a little thing. It's like this big. And what's important about an astrometric camera is that it has no moving parts and nothing changes. And so it goes on and off the telescope, so that changes. But it has no filter wheel, no other moving parts. It has a fancy detector that lets you read out fast on your bright star of interest and slowly on your reference field. And we've been able to get a lot of time on Carnegie's 2.5-meter DuPont telescope for the last 11 years. Happily, we now do the observations remotely. So after spending about 100 nights in Chile, now we can spend those nights in Washington, D.C. But there's probably 30 nights a year for 10 years that have gone into this project. So why do you want to do an astrometric planet search? The reason is that your sensitivity to exoplanets is different for an astrometric planet search than for a radial velocity search. So both the targets that you can do and the regime of planet mass separations that you probe are somewhat different. That would not be true if you launched a really fancy space mission like SIM or something, but for the ground. So this, for example, is TRAPPIST-1. So this is a paper that we published last year on the limits for an outer gas giant in TRAPPIST-1. So here's a population of known exoplanets. The blue curve is, there are 3 radial velocity observations in the literature of TRAPPIST-1. And so that's what my Monte Carlo simulation gives as the limits for the radial velocity planet that you would have been able to detect just given those 3 literature points. And those are near infrared radial velocity points. So they have uncertainties more like 150 meters per second or a couple hundred meters per second, not maybe the sub-meter per second that you're getting used to seeing for people doing G-type stars. Here's a more optimistic curve for what you would be able to do if you took more observations on a planet like TRAPPIST-1 with radial velocities. But it's a very low luminosity source, right? It's an M9 or something, right? So it's not an easy object on which to do radial velocities, even though it's close. This is our limit that we published last year for astrometry, which is not super impressive at this point. Our limit was about 5 Jupiter masses at a 1-year period and 1.5 Jupiter masses at a 5-year period. But you can see that it probes it's getting into a different part of the phase space of possible planets than the radial velocity observations are able to probe. So astrometry is particularly good at long period planets around low mass objects. So that's the sweet spot. And then this gives you a sense of the amplitude. So if you can measure an amplitude of a couple of 1 milliarc second, you could measure a Jupiter mass in a few-year period at a low-mass star that's at 5 to 10 parsecs. So that's the kind of scale that you're thinking about. It's not easy, of course, to measure 1 milliarc second amplitudes. And I would say the story of this project is in trying to beat down the systematic uncertainties to get better and better astrometry. So how do we do this? We take observations with our specially built cameras. So you have a field of stars. most of which are not stars that you're interested in, but everything in the galaxy moves. So they're all moving, both with parallax and proper motion. So these vectors are showing the amplitudes and directions of the proper motion. You have a star that you're interested in, which might be bright enough that you need to read out fast on that star, but you need to read out more slowly on your reference stars in order to get good enough signal to noise to carefully measure the location of this star compared to the locations of the other stars. And the pipeline for doing this was originally written by Guillaume and Glada Escudé, and now we have a postdoc, Tri Astradmaja, who's been working on refining that pipeline and really trying to get our uncertainties down, where statistically we think we should be able to do quarter of a milliarc second precision per epoch measurements, and then you can imagine dividing that by root n for the number of times that we observe these objects. We observe them about 3 times a year. We've been doing it for 10 years, so we have of order 30 observations on our best observed stars. We've been following about 100 stars to date, and so they range basically from about 15 to 30 observations per star. So you measure the motion of your object of interest relative to your reference field, and primarily, of course, what you see are parallax, which is this oscillatory motion, and proper motion, which of course the linear motion of the star. So you have to measure those and remove them, or you do a simultaneous fit for for position, the traditional 5-parameter fit for position, for proper motion, for parallax, and then on top of that for any additional orbital motion that might be the 2 objects. So I'll show you briefly the results on epsilon NDB and C, which were published just maybe a month ago by Serge Dietrich. So this is a known brown dwarf binary. So these are both T dwarfs. They appear, pretty typically on a color magnitude diagram, with the population of brown dwarfs that we know about. So, astronomy is a very patient field, okay? And this is the very patient person, Serge Dietrich, who's the first author of the paper, whose results I'm showing you right now. Because epsilon NDBC has a period of 11 years. So here's our first set of epochs. So these data, the red are the points from our astrometric planet search, and the blue points are the points from a complementary search known as CTIOPI that Todd Henry runs. And Serge did his PhD with Todd Henry's group, so he had access to both sets of data and was able to combine them. And they have higher uncertainties, higher per epoch, or lower per epoch precisions. They started observing a few years before we did, though, so that was actually critical for getting this 11-year period. So they started observing in 2004, I think. We started observing in 2007, and this paper takes the data through 2016. So grad students probably don't decide to do this for your thesis, right? But this is one of the few ways that we have of actually getting the masses of low mass objects, right? It's such a fundamental parameter in astronomy and so difficult to measure for non-young, just average objects in the near field, right? Nearby galaxy. Okay, so what you're measuring when you do this astrometry, though, is the measure of the photocenter, right? So if you have 2 identical stars, there's no photocenter measurement. So one way we can get fooled in our exoplanet search is by seeing a very low amplitude, but that very low amplitude could be generated by 2 M9.5, or T2 objects that are exactly equal brightness and therefore don't, when they orbit around their common center of mass, produce any motion of the photosphere whatsoever. So actually I've been following up all the objects that are bright enough to do with the Magellan AO system to make sure that we have a handle on the binarity. But anyway, this one was a known binary. So this is the motion of the photosphere. You then need to translate that motion of the photosphere into the barycentric motion, the motion of each object around its common center of mass. And that's very difficult if you don't have some adaptive optics image or some image that shows the flux ratio between the 2 stars. So the flux ratio is what sets how big the photocentric orbit is compared to how big the barycentric orbit is. But in this case, we do have those AO images that you saw taken at VLT and sitting in the archive. So you can actually now translate that flux ratio into the individual orbits of the 2 stars shown in the blue and the red dots, and the epochs of the adaptive optics images that we used are shown in these black lines. So this is how you do that. It's like a well-known classical astronomy thing. Okay, So it turns out that these objects were a bit strange in terms of their dynamical masses. They turn out to be 75 and 70 Jupiter masses. And if you look at most models for the hydrogen burning limit, they are at the low end of that. You don't really expect a 75 Jupiter mass object to be a brown dwarf in a lot of those models. It's really the models that are cloudless or cool very slowly, which would enable you to have that object be below the hydrogen burning limit. And we don't know at all the age of epsilon Indi. There are estimates in the literature that basically range from like 2 to 13 gig years. You can apply some filter to that, but it's a nearby star or nearby, there's a companion star, which is how most of those epsilon Indi A, those estimates are made. But it does have somewhat low metallicity, and so maybe it is really not able to cool very fast, and that can explain how you can get such high masses. So I showed you a couple of results, the TRAPPIST upper limit, the brown dwarf dynamical masses, that's all great, but what about the actual exoplanet search? I just want to leave you with a teaser. Stay tuned. So I hope these pan out, but we don't want to be the nth group to announce an astrometric planet that wasn't actually a real planet, so we're proceeding with a great deal of caution. But here, for example, is another object, from our sample, which is a mid-M dwarf, and we do see a periodicity of about 6 years. There are some worrisome outliers that I think we have to understand better before we're willing to claim that we actually detect anything. But if this 1.9 milliarc second amplitude were actually due to a planet, it would have a period of 6 years and a mass of somewhat under 2 Jupiter masses. Another advantage of astrometry being that you get the true mass and not a M sin I. So you can invite me back in a couple of years and hopefully I'll have something more definitive to say. Thanks. Yeah.
You have a much longer epoch of observation, but can you explain, in terms of parameter space, where you have an advantage over Gaia?
Right. Well, so Gaia will only have had has only had a duration of 5 years, and so, whereas we've had 11 years. So we are looking for those, preferentially for the planets that are even longer periods than Gaia. So out here, at many, many years. Gaia's precision for the faintest objects, for the brown dwarfs, is actually not much better than ours, or at least where we really hope we are at the end of Dr. Astrad Majha's attempt to improve our pipeline. So they do a little better. They certainly do way better for bright stars in terms of their astrometric precision. They don't do that much better for the M stars. I think we, would love to combine the Gaia data when they have not yet released the individual astrometric measurements. So at the point, we are using the Gaia DR2 as our reference frame for those objects. So happily we have a common epoch of observation. So we sort of have ground truth of where all the stars were at a single time when Gaia observed them. When they do release their actual astrometric positions, we'll combine them with ours. But we should be much more sensitive to the very long period things and the objects around the lowest mass, like the brown dwarfs and lowest mass stars that we look at, then Gaia would be alone.
Could you go from the first slide to the last slide?
Yeah. That one?
I didn't understand the difference between the blue and the red, but I did notice that most of the outliers, like you can say all the outliers, are red rather than...
Yes, red is flagging the outliers here. So that's the difference between the blue and the red. So our algorithm flags the outliers, right? So if you do a straight fit for the 12 parameter solution that we need to get the orbit and the motion of the star, most traditional fitting methods become very subject to the presence of outliers. And we get outliers for all kinds of observational reasons. Like we have not thrown out, any of the nights when the seeing was 2.5 arc seconds, and so we lost, half the reference stars in the frame because they were just too faint to observe well. We haven't thrown out, epochs where the telescope was accidentally defocused or anything like that. So one thing we're doing right now is going back to look at the outlier epochs and seeing if we can identify a reason that they would be outliers, because I don't like throwing out data points unless I think that they were not taken properly in some way. But yeah, the algorithm here is finding the outliers. And this is all done in, a giant Bayesian framework. And I could show you all the plots, but you don't want to see it.
Since you're coming from Washington, one, avoid, the color scheme, why do
I will not say anything about why the outliers might be in red. Red means stop, don't use them. Yeah. I'm sorry, I couldn't hear you.
The last point on the right, in the middle plot, looks like an out. No, middle plot.
Oh, this one. Right. So these are out. So there's a few things going on here. One is that there's been a giant MCMC that's gone into this, and the green orbits that are fitted are the mode of the values for each of the 12 parameters that the MCMC is considering. So it's not necessarily even the best fit model that comes out of the MCMC, right? Because you're just taking the mode of all the different 12 parameters and showing the model for that one. So that's perhaps one thing that's a bit misleading. The other thing is that it had to be an outlier. It's clearer here, where you can be an outlier by being an outlier in RA or in DEC, but it's most clear if you're an outlier or if you're an outlier in both. And other than that, I can't tell you. This one statistically didn't. By the way, if you can see very faintly underneath here, it's showing the distribution of potential fits from that cloud of fits from the MCMC. I can't really tell you why that one wasn't an outlier, except that it looks okay in declination. It just looks off in right ascension, and I guess that wasn't far enough off to have the algorithm flag it.
Thank you so much.
Yeah. I left it there. Oh, and now you get to listen to me hearing you. Sorry, here's the mic.
Am I audible? All right, great. Okay, so following up from Alicia's nice talk about the possibility of detecting a Jupiter mass object at wide orbit, here is a discussion about the difficulties in forming these wide orbit giant planets. And sort of the reason why it's difficult is because if you think about the origins of these planets, one way to form this is to start from the formation of the rocky cores. And that's the really limiting step of forming this rocky cores at wide orbits. Because if you look at the time scale of the coagulation, it just lengthens widely as you go farther and farther away from the star. So how do you calculate this? It's basically the collisional time scale. So it's the time it takes for a seed mass core to sweep up the material within the local annulus. So it's a function of the surface area, and it's also a function of the orbital period, both of which increases farther out from the star. So if you do the back of the envelope kind of calculation, if you want to form sort of a few Earth mass cores at around 5 AU, where we see our own Jupiter, it's going to take a multi-giga-year time scale, which is not good, because if you want to form gas giants, sort of by definition, you need to have these cores well before the disk gas dissipates away, which occurs over a few million-year timescale. And this is where the theory of pebble accretion came to an aid. So what exactly is pebble accretion? At the very core of it, it's simply a consequence of the gas particle dynamics. So that multi-gigayear timescale that I just told you about, you get that by assuming that the seed core presents a geometric cross-section. In other words, the incoming particles are energetic enough that their random velocities are larger than the surface escape velocity of this accreting core. But if these objects are sitting in some gaseous nebula, then the gas dynamical friction can damp away the random motion so that this gas drag can help these particles settle on to the accreting core. So when it comes to the efficacy of the gas drag, it's a strong function of how coupled these particles are to the gas, as quantified by this stopping time, which is simply the time it takes for these particles to reach terminal velocity in units of the local orbital time. And this accretion rate, so the rate at which you can help these particles settle onto the accreting core, that rate is maximized for particles that are marginally coupled to the gas. If the particles are way too well coupled, then they're just glued to the gas flow. And the whole point of getting pebble accretion is to get them off the gas flow to settle onto the core. If these particles are way too decoupled from the gas, then they're so large that you just go back to square one, where these particles just do not care about the gas, and the core goes back to presenting a geometric cross-section when it comes to collisions. So this accretion rate is maximized for the stopping time of about 1, which is this marginally coupled regime. But there's a problem here that if you think of the planet formation in a more global scale, then the same aerodynamic drag that helped these particles settle onto the core also helps these particles undergo rapid radial drift. So you may actually lose all these particles before you have a chance of growing into large cores. So based on these seeming difficulties in this competition between the global radial drift and the local concentration of the particles onto the seed mass, I recruited a phenomenal undergraduate student at UC Berkeley called Jonathan Lin, who basically quantified how easy it is really to form this massive cores at wide orbit using this new idea of pebble accretion. So he embarked on this rather difficult task of building a global semi-analytic model of planet formation where he evolved in tandem the gas disk evolution by viscous spreading, and also the evolution of the solid disk by the aerodynamic drag, as well as the growth of the core by pebble accretion, and also the gas accretion by the cooling, including the runaway gas accretion to build the gas giants. So without going into too much detail, because as you might imagine, pebble accretion is rather sensitive to all these different regimes of how the disk properties and also the particle properties. So just going straight to the results, this is what we get in terms of the mass of the planet as a function of final orbital radius with different colors corresponding to different starting radius, and squares correspond to the long-lived solid disk. The circles correspond to short-lived solid disk. And when I say short-lived, I'm talking about 0.1 million years. And the one thing that immediately struck out at us is that pebble accretion seems to be an all or nothing prospect. You either have really low mass planet or you have gas giant. So why is this the case? Why don't you have anything in between? There are many reasons, one of which is due to the scheme of the migration. But really, the most important point is that, at least initially, pebble accretion proceeds in an exponential rate. So why is it exponential? This actually can be calculated again, sort of like few lines back of the envelope calculation. Accretion rate is simply the the solid density times the accretional cross-section times the accretion velocity of the incoming particles. So it scales as the radius squared. Now you need to know this accretion velocity, and you can approximate the accretion velocity using the impulse approximation, where it's simply given by the acceleration due to the gravity of this accreting core times some relevant time scale. So the time scale here is not the usual encounter time scale that you have in classical impulse approximation. It's actually set by the drag time scale, because it's the aerodynamic drag of the gas that is the driving physics of pebble accretion. So combine all of that, then what you find is the accretion velocity scales as the mass of the core divided by the accretion radius squared. So put that back in here, you get that the accretion rate simply scales as the core mass, which of course means exponential growth. And that's exactly what we find. This also means the pebble accretion rate is exponentially sensitive to all the disk parameters, like the gas surface density, the degree of gas turbulence, the disk Mach parameter, as well as the stopping time. So how coupled the particles are to these disks. So based on all of that, what are the key requirements of Jupiter formation? So first thing is rather obvious. You need solid heavy disk to create more massive cores faster. But what's more important is that you also need relatively large stopping time and relatively low turbulence. So there's an issue with this requirement of the large stopping time. And the issue is that whenever we see these runs that successfully form gas giant, we see that the solid disk tends to drain out really quickly within a 0.1 million year time scale. So why is that a problem? So that is a problem because we see these large-scale dust structures in ALMA images of protoplanetary disk, which extends out to like 100 AU or tens of 100 AU scales over a few million year time scale. So it is true that we may have some observational evidence of this radial drift of the particles, where we see this size wavelength or size frequency relationship, where if you look at the longer wavelengths, presumably probing the larger grains, they tend to be more compact. However, none of the state-of-the-art drift coagulation calculations can get the exact shape as well as the SEDs right. So in other words, those calculations tend to result in way too efficient of a radial drift. So what are some alternatives? Like, is there a way to fix this and have some and make the Jupiter formation in agreement with the currently observed populations of protoplanetary disk? So one idea is to have this particle traps where the local pressure maxima within the gas disk tends to collect all the solid particles within that maxima. However, there are some remaining questions, and for me, there are these two questions that I have. So one question is that it's not yet clear to me whether the presence of this particle traps will help or actually hurt pebble accretion, because by definition, once you approach this pressure maxima, the relative velocity between the gas and the dust tends to approach zero. So it's not clear to me how you calculate the accretion velocity as you approach this pressure maxima. Another question that I have is, it's again not clear to me at all whether the traps will survive through the formation of planetary cores. And in the field of planet formation, many people would say that, oh, there's a pressure maximum, you just collected all the solid particles, you must have some planet formation there. But as you form these massive cores, those cores actually perturb the background disk, so you might destroy these traps, and it's not clear what exactly will happen. So these are some of the things that I'm currently investigating with Phil Hawkins and his graduate student at Caltech, but I'm also really interested in hearing your thoughts. Thank you.
Mm-hmm. And these are formed hydrodynamically, have nothing to do with the core formation,
right.
Planetesimals. So why is this dismissed as a channel towards making Jupiter like a planet?
Yeah, so there are sort of two reasons. So one reason is that they tend to create too massive of an object. So something that approaches masses larger than 10 Jupiter masses. But another more physical reason for that is for these protoplanetary disks in the disk setting. Yes, you do cause this turbulent fragmentation, but they do not survive because you need to also cool them down fast enough so that they will actually survive against the shearing within the disk.
And so in the models you used for the pebble accretion, are those built out of analytical estimates, or is there more that you? I don't know. Is there any more you can do than just estimating the growth, or would that even help you?
Right. So what we use is the analytic calculation. So it's basically Ormel-Clark 2010, but we augmented using the effect of turbulence. So turbulence will stir up the scale height of the particle disk. It also changes the relative velocities between the particles and the gas. But you're right. Some people actually do like hydrodynamic simulation with pebbles to see how much pebbles you accrete onto some seed core. And people like Duane and Ruth Murray Clay, for example, they've actually implemented turbulence within the disk self-consistently using MRI. So people do it, and what they find is, in general, they do agree within order of magnitude with this analytic calculations. But like what is not obvious is, those are assuming some just like general background disk with some level of turbulence. But if you have some like really dramatic features like pressure traps, I haven't seen any calculations of what exactly happens in those cases.